I work for Ampere, and so I'm excited to be here and just kind of, this is a birds of a feather session. So part of it is a little bit, part of it is trying to discover new things about software, new applications and new ways of optimizing, but then also share your ideas and also find ways we can collaborate. I think that's so important with the ARM ecosystem. We all have our own products, our own software, whether it's software or hardware products, but to really help the industry move forward when it comes to ARM64, for example, I think a lot of this collaboration is so important because, in some ways, we kind of follow the topic that we had today about data mining. I feel like sometimes I'm data mining what's been done before, right? I find out like, someone from XYZ company made a change that actually helps ARM64. This is great, but I didn't know about this, So these are all kind of pieces of the puzzle. So PHP and HHVM. So it's been HHVM has played a valuable role in the evolution of PHP. I think, there's an Irish saying that hunger is a good sauce. And an HHVM, and PHP is hungry. When HHVM came on the scene, it grew from an initial PHP to C++ compiler, released in 2011 as the hip-hop virtual machine. Basically another JIT generating machine code from bytecode. They saw incentive, they wanted to prove themselves. They saw incentive in achieving parity and delivering compatible PHP 5 results. And together with HHVM, they also released Hack, which is their programming language of preference with their own applications in-house. So in some ways, it supporting PHP spurred Facebook on, but it also spurred the PHP maintainers on, as you'll see with PHP 7 and eventually their own JIT, a new optimized JIT. So in 2017, HHVM team announced a parting of ways, so to speak, with the growth of PHP 7 and continuing their own development in support of Hack. In my mind, it's kind of a friendly separation if you think about it. I think both have benefited from their collaboration. The HHVM JIT can be broken down into 4 parts. Basically, type specialization, profile-guided optimizations, side exits, and region-based compilations. The type specializations relates to getting that sort of information on the types and the granularity for specialized use cases. The profile guided optimizations are sort of a class of optimizations, can either be enabled or enhanced by the use of runtime information. So these are things both internally in the design but also externally as well at an application level for workloads. Side exits are basically uncommon traps, but it gives the JIT the ability to leave a compilation unit and transfer control elsewhere. And that's important because of the region approach that they take. So it's a region-based compilation, and code generation in HHVM is based on that. So they're not restricted to entire methods, single basic blocks, or straight line traces, so they can move objects around. That has implications, though, on ARM. One of the challenges with ARM, I'll highlight a little bit, is in terms of relocation of code. How do they test it? They use an open source benchmark suite. The goal is to provide a benchmark suite testing something representative of real world situations. The main suite runs Nginx, Siege, and PHP, PH7, HHVM over fast CGI, over a TCP socket. And it's as close to identical as possible. They want to just keep things basic, but they want to be able to really exercise transactions. And it'll run up to 300 warm-up requests, as many requests as possible in 1 minute. Statistics are only collected once the model is warmed up. It generates fairly reliable synthetic benchmarks for purposes of profiling these popular applications. And when you work with Facebook or you're looking into analyzing your own SOC, your own system's performance, it's a relatively consistent measure of how well you're doing. Siege is the actual engine. I think that's actually an appropriate name. So often when we do development, we work with different test benches, that we really need tougher names, I think. I kind of like Siege as a name. Basically, it's an open source regression test and benchmark utility, so it can stress test a single URL. You can run it either dynamic or cache tests, and it runs its tests from only one server. It runs from the command line, and it's relatively painless to set up and install. And it's easy to sort of customize in terms of your own environment, and also if you have your own continuous integration and continuous delivery system as well. So it fits nicely within that for your own hardware development. It reports the total number of hits recorded, bytes transferred, response time, concurrency, and return status. And more importantly, a transaction is characterized by the server opening a socket for the client, handling a request, serving data over the wire, and closing the socket upon completion. And that's the synthetic benchmark in a nutshell. So when I approached the HHVM code base, you know, coming at it as someone new to the code base, it's sort of like peeling an onion as you go about it. And part of this birds of a feather session for me was to kind of just highlight, hey, how we were exploring HHVM, how we went about looking at some of the code, and how we looked at different optimizations. So one of the initial focus was on the OS and tools. So one area was profile guided optimizations, right, with GCC, being able to compile the application, train the application, be able to capture that and use that training based on different workloads. And the workloads in this case could be Drupal, it could be MediaWiki. So you can use PGO to train it for exercising, before you actually run the tests, right? The other thing that we used was enabling use of low pointer. And basically, low pointer is a feature, a flag, so to speak, that allows you to use compact objects with members that are guaranteed to point to low memory. And there's some other optimizations in there as well that's a benefit. Enabling, if your SoC supports hardware-based CRC, then it's also possible to enable that through a CMake flag within the code base as well as your GCC compiler, right? So that's already supported in there. And then set up some pre-run optimizations. It's always a good idea before you do your runs to set them up in terms of flushing caches, giving the kernel the ability to reuse TCP ports, which may be in a sort of time-wait state. Disable address randomization, virtual address space. You know, these are just all fundamental things that you need to kind of unroll and get going on your system. Yeah? About flushing the caches? So, so depending on your architecture, you should have an ability to drop the caches, and there's a kernel. There's actually a way through sysfs to actually do that, to actually cause a flush of like your L3s, for example, and so that's your LLC, so to speak, I should say. But there is a way through the kernel API. It's a simple sysfs control to actually just cause the caches to be dropped. It's basically trying to get your system into a baseline state. So my goal with optimization scripts are to get it into a well-performing and known configuration, because everything I'm doing is I'm trying to get it to a point where we can reproduce this consistency and results and getting it into a CI system. With the goal, once it's in a CI system, is then you can build your kernels, and as you pull in a new updated kernel from upstream, as there's a new RC candidates from Linus, you pop you push your kernel, your patches that are either pending or not yet upstream onto it, and then you can exercise this as a benchmark to catch regressions. Yes? It does PGO, but it's not doing PGO in the sense that you're thinking. I think they're using profile guided optimizations, but I think that within their own application, they have, as a part of their JIT, they're actually doing some little tests, right, of different regions or objects, and that's what I meant. Something like OpenJDK might do as well, but it's, when I say PGO there, I'm at the higher level, which is GCC. Right. What am I using for PGO? Yeah, so basically I'm just using a GCC 8.2 compiler, and I'm using the specific GCC supported flags for training and instrumentation, and then using the profile. So you first compile it with training as well as instrumentation, and then you do a run, and then you get the PGO data, and then you do the use compile flag, which tells it to use the PGO data, and then you run your tests. In some cases like that, we could see 3%, in the ballpark of 3% or so. Something like what? Yeah, with MediaWiki and things like that. In general, it's sort of that's a useful way of doing some benchmarking, not just with HHVM, but also with other types of projects as well, which GCC might make use of. But then incorporating with that are setting up the caches, basically trying to make something reproducible, flushing the caches, setting your environment. Now the optimization focus. So one of the things you want to do is you want to start to look at the whole landscape, so to speak, of the code base. So as a memory allocator, HHVM uses JEmalloc. And actually, it always behooves you to go look at the particular ingredients, especially when it comes to memory allocation, because a lot of times when it comes to servers, a lot of the optimizations are all about memory. It's about a memory engine and how efficient it is and how it takes advantage of your own hardware. And so fortunately, there's been a lot of changes in the past year even to improve JEmalloc. It used to have a problem with instruction cache starving with JEmalloc in the past, and I think that has actually been fixed. But there's other things you can do. One thing in particular with JEmalloc and HHVM is you can statically link it. And that can give you at least a few points of percent improvement, like 1 to 2 to 3% improvement by statically linking JEmalloc. There's also things you can play with in terms of number of areas that JEmalloc spawns. You can, how often things are made dirty and the defrag rate and things like that. But it's always good to take a look at JEmalloc and see what changes have been made and go from there. Then the other thing is that making use of huge page support. To my knowledge, HHVM doesn't really support madvise like OpenJDK does, so it's a good idea to experiment with large page sizes in particular. And from this, I could get at least another 3% to 4% boost by using 64K pages with 512 megabyte, huge page size, which is kind of interesting too, because when you pay attention to different distributions, I didn't really talk about distributions here, but when you think about the landscape in the server market in particular, you've got CentOS, Red Hat Enterprise Linux, you have SUSE Linux, and you have also Canonical, as well as Debian, I'm sure. So I used actually Fedora, so I'd use Fedora 28 on this, just because for me, it's the upstream of CentOS, so to speak, and also Red Hat Enterprise. And I like to be, what's important for me when I work with these code bases is that I have a proximity, so to speak, to upstream and to facilitate bringing in newer pieces of software. The other thing is investigate memset, memcopy optimizations. So the code base within HHVM has a number of different copy routines. Some of them actually are inline assembly for ARM as well as x86. That's always another good topic, is that when you look at a code base for a software project, see what optimizations have been done so far for x86, right? Get an idea of what's been done there, what's not been done for ARM. Where are the gaps, so to speak? What are they taking advantage of that we perhaps should be taking advantage of as well? Do your own homework, so to speak. And so I looked at a memset implementation, a memcopy improvement over glibc 2.27, but it was kind of a wash. The reason is that my update for that didn't do so well, especially in HHVM where they have a lot of mixed size copies from destination and source. A lot of mixed alignment changes there. But it's always a good idea to experiment. See, don't necessarily assume that glibc is going to give you the best you want. And in some cases, if they have separate 8-bit, 16-bit, 32-bit copies or things like that, it might behoove you to consider some inline assembly or something like that, just to take a look at it. But that also should come out of your profiling. Evaluate your cache performance. And also keep in mind with ARM limitations on branching and address ranges. Profiling, fortunately about a year ago, somebody added support for translation cache printing, which is a way for you to be able to get sort of like the opcode. You can actually profile the functions as well as get inline assembly annotation. For the top functions, like the top 20 functions by cycles, the top 20 functions by size or time. And with that, it's a very useful tool when it comes to working with their JIT. Actually, a lot of the optimization I've seen downstream from the JIT is in VASM. And so VASM is like, after VASM, you go to VXL, and then you've got basically the bytecode, the machine code, right, with HHVM. But there's a lot of ARM optimizations there. But and then perf, of course, looking at, like if you're looking at your cache performance and you're looking at things like that, take a look at perf and flame graphs as well, which you can generate from your perf record data, which kind of gives you an idea of your call stack, but also how much time you're spending. But then you have to know the code base. So it's important to know the code base. If you're spending a lot of time in something, you need to understand, is it important for me to spend a lot of time in here? And that's why also, comparing to x86 as well. So some observations I made. PHP, looking at PHP, Zen lacked support for AARCH64 GCC global variables, which I found really surprising that no one had patched that. Where the global variables help is that they can be substituted for arguments to the handlers by storing them in global registers. So Zen has a number of different modes that you can use, and some of them, like the call type modes, which are kind of like a callback, can make use of those global registers, and x86 was already using that. I think I had a developer submit a patch for that, but I don't know if it's up there yet. Limitations on immediate moves. So I saw a lot of things like this, which isn't good, right? Look at that. I mean, come on. 3 instructions versus 1 example. So that I got from TC print, where I was looking at the functions, translating from their cache, the top 20 functions in HHVM, looking at the annotation, and then doing the same thing on a Intel Silver, right? So seeing things like that, right? Concerns there. Limitations on conditional branches as well. So as you know, unconditional simple relative branches can be upwards, downwards of 128 megabytes, right? But conditional branches only have a range of about 1 megabyte. And that can be costly in the JIT for a region-based JIT. So a region-based JIT will take objects, which are the code, and try to relocate it, right? But if it relocates it out of range, then we have a problem. With the x86, when hot cold splitting occurs, that relative short displacement conditional branch instructions are changed to larger displacement conditional branch instructions, but it's a little more costly for us. And actually, I think there was a recent commit in HHVM source that actually disabled that for ARM. But again, needs to be. And the other thing to look at is your cache topology and size. Let's see how I'm doing. Actually, I'm doing pretty good. I ran over a little bit just because another gentleman had to talk and he had to move in here, so that's why. Take any questions on some of the work with HHVM? If anybody has anything.
Yes, just one quick question. So you mentioned profiling, but you also said to take hints from x86, what they've improved. When you've looked over it, like just for HHVM, where has profiling been more useful, or has the x86 optimizations been as useful? Or?
In the case of HHVM, its profiling is more useful than looking at x86. The thing about Facebook is that the open source Facebook is not the same, the open source HHVM is not the same thing as the internal HHVM at Facebook, I'm almost sure. So you don't know necessarily what optimizations Intel really does internally with Facebook anyway. So all you have to go on, it's good to take a quick look at any sort of if-def, x86, you know, in there, just to take a quick scan, take a look at the commits, but definitely the perf analysis is the heart of it. But I really don't know where it's headed, you know, because it's clearly a separation of ways with HHVM and PHP. And to my knowledge, there's no significant application base for hack, right? So I think HHVM is important, and hack is important to Facebook, absolutely. And so therefore, ergo, if you make hardware, HHVM is important to you too, right? But in the open source community, in terms of the mind share, I don't see hack as being a part of the ecosystem and I think Facebook is going to try hard to try to grow that mind share, but you know, so I think it's important to be aware and to also improve over time HHVM. Thank you.